Good morning, students. My name is Sharmila, working as an assistant professor in EC department in Erode Secondary Engineering College. I am handling antennas and wave propagation. In this, I am going to give detailed explanation of antenna parameters because antenna parameters plays major role in fixing an antenna. Okay. Next, these are the content to be discussed below. First and foremost thing is a radiation pattern, then radiation intensity, radiation density, beam width, directivity, antenna efficiency, gain and polarization. Next, the radiation pattern. In this radiation pattern, whenever the current passes through the antenna, it radiates. These radiations are more particular in one direction, in rest of other direction. This property is known as the radiation pattern. It is also called as antenna pattern. If the radiation from an antenna is represented in terms of power per unit area, the resultant pattern is called as power pattern. If the radiation from an antenna is field strength means, then the radiation pattern is called as field pattern. Okay, clear? Then this is the traditional pattern is shown in the figure. Okay, the radiation pattern is a three-dimensional figure. Generally, spherical coordinate system is used to describe the radiation pattern. Here, the antenna is located at the origin of the spherical coordinate system. Then, major lobe and minor lobes are discussed below. Then the next content is the radiation pattern lobes. Radiation pattern lobes are major lobes, minor lobes, side lobes and back lobes. Depends on the field strength, the radiation lobes can be classified. First lobe is the major lobe. This is the radiation lobe containing the direction of maximum radiation. It is also called as the main lobe. The maximum power is transmitted to free space from an antenna only by major lobes. Depends on the types of antenna, there is a possibility to have more than one major lobe in a pattern. Next, minor lobe. All the lobes other than the main lobes are called the minor lobes. These lobes represents the radiation in undesired direction. The level of minor lobe is usually expressed as a ratio of power density in that lobe to that of the major lobe. Okay. In most wireless system, minor lobes are undesired. Hence, a good antenna design should minimize the minor lobe. Next one is the side lobe. These are the minor lobes adjacent to the main lobe and are separated by various nulls. The side lobes are the largest among the minor lobes. Then back lobes. This is the minor lobe diametrically opposite to the main lobe. It is a radiation lobe whose axis makes an angle of approximately 180 degree with major lobe direction. Then radiation pattern can be classified as three types. That is, first one is the isotropic antenna, second one is the directional antenna, third one is the omnidirectional antenna. In isotropic antenna, an isotropic radiator is an ideal antenna source which consists of small element that radiates equally in all directions so that its vertical and horizontal radiation patterns are circular and produce a beam width of 360 degree in both the planes. Okay, clear? Then directional antenna. When an antenna has the property of radiating and receiving electromagnetic waves more effectively in some direction than in others, the antenna is called as a directional antenna. Its main beam is usually narrow, that is, it has reduced beam width. Next one is the omnidirectional antenna. Omnidirectional antenna, it is an antenna that radiates equally in all direction in a given plane. Okay. These are the explained here. Isotropic antenna. Next one is the omnidirectional antenna. Omnidirectional antenna is a circular shape. Radiates in equally radiate in all directions. So it is a circular shape. Then it is a directional antenna. Directional antenna is a radio frequency wireless antenna designed to function more effectively in some direction than in comparatively other direction. Okay. Next one is the principal patterns. Principal patterns is also called as planes. It has two types, E plane and H plane. In the E plane containing the electric field vector and the direction of maximum radiation. Or else the H plane, the plane containing the magnetic field vector. Here E plane electric field vector, H plane is the magnetic field vector and the direction of maximum radiation. Then the field regions. Field regions have far field region, reactive near field region and radiating near field region. Far field region is a Fraunhofer zone. Radiating near field region is the Fresnel zone. Next is a directional antenna. Next radiation intensity. Radiation intensity, it is denoted as U. Power radiated from an antenna per unit solid angle, that is power divided by solid angle. The unit is watts divided by steradian. Steradian is it does not depend upon the directly proportional to the square of the distance is a steradian. Next, the formula for radiation intensity is U is equal to R square into W radiant. U is the radiation intensity, W radiant is the radiation density. Okay. Next one is the radiation density or radiation power density. It is denoted by W bar. Power radiated from an antenna per unit area. That means power divided by area is a radiation density. The units are watts divided by meter square. Power is denoted by watts, then area is denoted by meter square. Radiation density is depends upon the directly proportional to the square of the distance. The equation of the radiation density is W is equal to E into H. E is the electric field, H is the magnetic field. Okay. Next, W bar is the power density. Next, beam width. Beam width is the aperture angle from where most of the power is radiated. In order to compare the directivity of antenna quickly, beam width is useful. For any pattern, beam width is defined as the angular separation between two identical points, that is P, for consider P and P dash on the opposite side of the pattern maximum. In an antenna pattern, a number of beam widths are defined, that is half power beam width and first null beam width. Okay. The two main constituents of this beam width are half power beam width and first null beam width. Okay. Next, half power beam width. Half power beam width is defined in a plane containing the direction of the maximum of a beam by the angle between the two directions in which the radiation intensity is 1/2 of the maximum of the beam, that is a half power beam width. Next, first null beam width is the angular separation between the first null of the pattern. Both half power beam width and first null beam width are demonstrated for here. Half power beam width is a angle between the two directions in which the radiation intensity is 1/2 of the maximum of the beam. First null beam width is the angular separation between the first null of the pattern. Okay, clear? Next, effective length. Effective length. It represents the effectiveness of an antenna as radiator or collector of electromagnetic energy. Okay, an antenna can radiate or receive effectively to that of the particular distance called as effective length. I will repeat again. An antenna can radiate or receive effectively to that of the particular distance called as effective length. it is denoted by LE, that is effective length. Mathematically, it is a ratio between open circuit voltage to the incident voltage. Incident field strength. The L is equal to V by E. V is the open circuit incident voltage. E is the incident field strength. Okay. Next is the directivity. Next one is the directivity. Antenna does not radiate equal in all directions. So we have to find the directivity. Ratio of maximum power density, that is P of theta comma pi maximum to its average value over a sphere, is called as directivity. That is denoted by D is equal to P of theta comma pi maximum divided by P of theta comma pi average. This is the directivity equation. Next one is if the direction is not strictly specified, the direction of maximum radiation intensity is implied. Okay. Next, the gain. The gain of an antenna in a given direction is defined as the ratio of intensity in a given direction and the radiation intensity that would be obtained if the power accepted by the antenna were radiated isotropically. This is also called as absolute gain. The gain formula is G is equal to, the gain is denoted as G. G is equal to neta into D. Neta is the efficiency, D is the directivity, G is the gain. If the gain decreases means emits radiation in all direction. If gain increases means radiates in particular direction. Okay. Next one is the beam efficiency. Beam efficiency of an antenna may be defined as the ratio of power radiated within the main beam to the total power radiated. The beam efficiency is derived for ideal rectangular and circular apertures as a function of the edge to center amplitude ratio. First we have to find the total solid angle, that is denoted as ohm A is equal to ohm capital M plus ohm small m. Ohm capital M is the solid angle for major lobe. Ohm small m is the solid angle for the minor lobe. Then beam efficiency is equal to main beam angle divided by total beam area. This is denoted by epsilon m is equal to ohm m divided by ohm A. It has no unit. Okay. Next, antenna aperture. The antenna aperture is the area whose orientation is standard towards the direction from where the electromagnetic signal is coming. So this can be done to interrupt the equal power from the incoming electromagnetic signal as it can be emitted through the antenna which is receiving it. Next, the antenna aperture helps to find how effective an antenna is at a receiving station. Antenna aperture can be denoted as epsilon AP. Epsilon AP is equal to AE divided by AP. AE is the effective aperture, AP is the physical aperture. Horn and parabolic antenna has a 50 to 80% of antenna aperture. Large dipole antenna has a 100% of antenna aperture. Next, the side lobes decreases means antenna aperture is also decreases. Okay. Next one is the polarization. Polarization is the alignment of the component of electric or magnetic field is called as polarization. This wave consists of electric field or magnetic field component. Next, polarization is the orientation of the electric field or magnetic field. Next, if need only vertical component, it restricts all other direction. It is called as a polarization. Time varying behavior of the electric field strength vector at some field point in the space. Okay. Polarization has three types, that is linear polarization, circular polarization and elliptical polarization. In linear polarization, electric field as a function of time remains along a straight line. That is a linear polarization. It may be only Ax component or Ey component. Both Ex and Ey component in phase. That is a linear polarization. Next, elliptical polarization. Elliptical polarization, electric field as a function of time traces a ellipse. That is E1 not equal to E2, del is equal to 90 degree. Okay, this is also called as clockwise polarization. Next one is a circular polarization. When electric field as a function of time traces a circle is called as circular polarization. For condition is E1 is equal to E2, del is equal to 90 degree. Then right hand polarization is the clockwise direction and left hand polarization is the anti-clockwise direction. Okay students, thank you. We will see, hope you understand this antenna parameters very well, I think. Okay, next class we will see another importance in antennas and wave propagations. Okay, thank you. Good evening friends. Next topic we are going to see folded dipole antenna. In general, what is meant by dipole antenna? Dipole antenna, also known as doublet or dipole aerial. It is defined as the type of radio frequency antenna, and it consists of two conductive elements such as rods or wires. Then the dipole antennas are the very simplest and most widely used type of antenna. A dipole means, name itself we note, two poles. Dipole means two poles. Hence, the dipole consists of two identical conductive elements such as rods or metal wires. This length of the metal wire is approximately half of the wavelength. What is meant by half of the wavelength? Lambda by 2. Lambda is the wavelength. Half of the wavelength means lambda by 2 in free space. Next, this wire or rod is split at the center and the two sections are separated by an insulator. Okay. Two sections are separated by an insulator. These sections are known as the antenna section. By this antenna section only, we are going to give the supply. Supply means what is? That electromagnetic waves or electric signal or magnetic signal. These two antenna sections are connected to a feeder or coaxial cable at the end closest to the center of the antenna. This is the basic dipole antenna. Okay. Next, from this, we are going to see the folded dipole antenna. Folded dipole antenna is an antenna with two conductors connected on both sides and folded to form a cylindrical closed shape. That means two dipole antennas connected parallel to form a cylindrical closed shape, but to which feed is given at the center. That is called as antenna section. Same compared to dipole antenna, the folded dipole antenna is also same feeding point. Okay, but in this folded dipole antenna, we are using two parallel dipoles. Next, the length of the dipole is half of the wavelength. Same for both dipole and folded dipole antenna. The length should be half of the wavelength. So it is also called as half-wave folded dipole antenna. Then the directivity of folded dipole antenna is bidirectional. Directivity means radiation pattern. The radiation pattern and beam width and gain should be high. Then only the antenna should be a perfect matched. So the antenna radiation pattern should be bidirectional. Then the input impedance is also higher. Next, in general, The frequency range of folded dipole antenna should be 3 kHz to 300 GHz. This is mostly used in television receivers. Next, if the radius of the two conductors, because we are using two conductors, two dipole antenna, so the radius of two conductors are equal, then equal current in both the conductors in the same direction. That is, currents are equal in magnitude and phase in the two dipoles. Okay, the total power developed in the folded dipole is equal to that developed in the conventional dipole. The conventional dipole and folded dipole total power should be equal. Therefore, the input or terminal impedance of folded dipole is greater than that of the conventional dipole. Input or terminal impedance should be greater in folded dipole antenna. Okay, it can be proved that input impedance at the terminal of a folded dipole antenna is equal to the square of the conventional dipole. The input impedance at the terminal of folded dipole antenna is equal to the square of the conventional dipole antenna. Okay, clear? Next, in folded dipole antenna, the frequency range should be 88 to 108 MHz in FM broadcast receiving. Okay, next, 54 to 260 MHz in TV antenna. The frequency range should be in folded dipole antenna. Next, the figures are first figure A shown in folded dipole antenna. Next, figure B will be a transmission line mode. Figure C is a antenna mode. First, in general, folded dipole. Figure A, see the figure A. In this, I already said, right? Folded dipole antenna is a two parallel dipole antenna connecting parallel with radius and length L. Okay, from this we are keeping our antenna at the center of the feeder. Okay, next, it contains, the folded dipole antenna contains two types of modes. One is the transmission line mode and another one is a antenna mode. In transmission line mode, the antenna current denotes by IT. In antenna mode, the antenna current will be denoted as IA. In transmission line mode, the currents are in opposite direction, but in antenna mode, the currents are in same direction. Next, the folded dipole and regular dipole. This is the basic difference between folded dipole and regular dipole. Both are half of the wavelength. The length of the dipole contains half of the wavelength, that is lambda by 2. But in this folded dipole antenna, we are applying the current, but we got two types of radiation. That is, one conductor which should produce one radiation, another conductor will produce another radiation. But in regular dipole, it contains only one radiations, that is ID current applied to the center of the dipole. It gets one type, only one radiation. This is the basic difference between folded dipole and regular dipole. Next, this is the basic equations of folded dipole antenna. First, we are applying the half of the voltage, that is V by 2. Then we are applying Kirchhoff voltage law. I1 impedance Z11 plus I2 Z12. First, we are going to take the common. If here we are using I1 current is equal to I2 current, so apply I2 is equal to I1. So substitute I1, taking common terms outside. So I1 should be common. I1 into Z11 plus Z12. Z11 is equal to Z12 is also equal. So V by 2 is equal to I1 2 into Z1. Here Z1 value should be um, in dipole antenna Z11 is equal to 73 ohm. So substitute V by I1, taking this numerator term into denominator term. V by I1 is equal to 2 cross multiplication we are using 2 into 2 Z11 2 square, then Z1 value should be 73 ohm. So 4 into 73 ohm we get 292 ohm. Here we are using only 2 dipoles, so V by 2. Next time we are using 3 dipoles, that is V by 3 is equal to I1 Z11 plus I2 Z12 plus I2 Z13. Taking this I1 is equal to I2 is equal to I3 is equal to I1. So substitute I1 common. So Z11 plus Z12 plus Z13. Next also Z11 is equal to Z12 is equal to Z13 is equal to Z11. So we have 3 Z1. Next add 3 Z11. So we get I1 into 3 Z11. Again we are doing cross multiplication. So we get 3 comma 3, that is 3 square Z11. The Z11 value should be 73 ohm. 9 into 73 is equal to 657 ohm. Next, in this radius, we are going to find the radius. R2 is equal to 2R1, that is R2 should be 2 times of R1. Then Z is equal to Z11 into 1 plus R2 divided by R1 the whole square. Z11 value should be 73 ohm into 1 plus 2 R1 divided by R1 the whole square. Next substitute these R1 and R1 cancel, gets cancelled. So 1 plus 2 should be 3. 3 square should be 73 into 9, 657 ohm. Next we have to find this equation in logarithmic, that is Z is equal to Z11 into 1 plus log A divided by R1 divided by log A divided by R2 the whole square. We get Z11 into Z ratio. This is the basic equation of the folded dipole antenna. Next, this is the half-wave dipole antenna, the current distribution. Current distribution should be at the center. This uses the feed line at the center, then this uses only half dipole antenna. Next, this is the radiation pattern of dipole antenna. The side, this is the side view, and this is the next one is the top view. In side view picture, we get only 2 degrees. 0 degree and 180 degree contains maximum radiation, others are the minor radiations. Next, the advantages of the folded dipole antenna. Advantages are, the first point is the reception of balanced signals. What is meant by balanced signal? Balanced signal means, for example, in transmitter and receiver, the transmitter sends some energy to the receiver side. The receiver side will also transfer the energy to the transmitter. This is vice versa process. This is called as balanced signals. Next point is receive a particular signal from a band of frequency without losing the quality. Next, a folded dipole maximize the signal strength and high input impedance. Wide band in frequency acts as built-in reactance components network. These are the advantages of the folded dipole antenna. Next, disadvantages. The following 2 points are the disadvantages of half-wave folded dipole antenna. That is, first one is the displacement and adjustment of antenna is a hassle. Next one, outdoor management can be difficult when antenna size increases. Next one, applications. These are the applications we are going to explain now. The following mainly used as a feeder element in Yagi-Uda antenna, parabolic antenna, turnstile antenna, log periodic antenna, phased and reflector arrays, etc. We are going to study the unit 4. These are the applications are going to see. Next applications is generally used in radio receivers, most commonly used in TV receivers. Next, okay, what we all discuss now? A fold dipole antenna is a modified lambda by 2 dipole with an additional wire connecting its two ends. Okay, clear? The folded dipole antenna is an extremely practical wire antenna and is also called an ultra closed spaced array because there is no open end. At the center only we have open, but here we are giving the supply, that is antenna feed point. It consists of two parallel closely spaced lambda by 2 dipoles jointly together at the outer ends forming a narrow wire loop. Okay, the antenna is fed at the center of one dipole, that is the dipoles have the same voltage at their ends. As well as the radiation fields are concurrent, it is the same as the lambda by 2 dipole antenna, but input impedance differs and it is equal to 300 ohm. Next, folded dipole antenna differs from the conventional dipole mainly in two respects. What is that? Directivity and wider bandwidth. The directivity of folded dipole antenna is bidirectional, but because of the distribution of current in the parts of the folded dipole antenna, the input impedance becomes higher. However, the radiation patterns of both are equal. What is the radiation pattern of folded dipole antenna and conventional dipole antenna should be equal. Okay, I think you all clear now what is meant by folded dipole antenna. Okay, next topic, Yagi-Uda antenna. Yagi-Uda antenna is the most widely commonly used type of antenna for TV reception over the last few decades. Okay, clear? Yagi-Uda antenna is the most common widely used type of antenna for TV reception over the last few decades. We are seen in our school days, we are using just BPL TV. In that BPL TV we are using one antenna that is like this, right? So the folded dipole antenna should be the Yagi-Uda antenna should be our TV reception. Next, it is the most popular and easy to use type of antenna with better performance, which is famous for its high gain and directivity. It is very famous for its high gain and directivity. Then the frequency range. Frequency range is very important for sending the data that is sending the electromagnetic waves from one place to another place. So the frequency range is very important. The frequency range in which the Yagi-Uda antenna operates is around 30 MHz to 3 GHz, which belong to the very VHF means very high frequency and UHF means ultra high frequency bands. Next, center should be a folded dipole antenna because we are connecting two parallel dipoles that forms a narrow closed shaped loop, that is the folded dipole antenna. Then remaining like a stick now, that should be a dipole antenna. Next, third diagram should be first center dipole, first one center at the right director and backside reflector. Next, some specifications are given or followed. One can design a Yahuda antenna. In Yahuda antenna, we are going to design a Yahuda antenna means we are already learned something about this specification. First, the length of the driven element should be 0.458 lambda to 0.5 lambda. Then the length of the reflector should be 0.55 lambda to 0.58 lambda. Then the length of the director 1, because in TV antennas we are using multiple reflectors and directors. So director 1 we are using, director 2, director 3 all we are using. Length of the director 1 should be 0.45 lambda. Then the length of the director 2 should be 0.40 lambda. Then the length of the director 3 should be 0.35 lambda. Spacing between all the directors should be 0.2 lambda. Reflector to dipole spacing should be 0.35 lambda. Dipole to director spacing should be 0.125 lambda. Next, general characteristics of Yahuda antenna. It contains 3 elements array, that is 1 reflector, 1 director and driven element. Driven element is a center element, that is a antenna feed element. Then such type of antenna is generally referred to as a beam antenna. Next, it has unidirectional beam of moderate directivity with lightweight, low cost and simplicity in feed design. It has unidirectional beam of moderate directivity with lightweight, low cost and simplicity in feed system design. With the spacing of 0.1 lambda to 0.15 lambda, a frequency bandwidth of the order of 2% is obtained. It provides gain of the order of 8 dB or front to back ratio of about 20 dB. It is also known as super directive or super gain antenna due to its high gain and beamwidth per unit area of the array. An antenna or array which provides directive gain, appreciable greater than that obtainable from uniform distributions is known super directive or super gain antenna. If greater directivity is desired, further elements may be used. For example, 5 or 6 elements are used with case, and arrays up to 40 can be constructed. It is essentially a fixed frequency device that is frequency sensitive, and a bandwidth of about 3% is obtainable. This much bandwidth is sufficient for television reception. Next, this is the radiation pattern for Yahuda antenna. First one is a horizontal pattern and second one is the vertical pattern. In horizontal pattern, in the direction of 0 degree, it contains maximum radiation, but in vertical pattern 0 degree it contains only minimum radiations. Next, voltage and current relations in parasitic elements. First one, it contains 3 directors because that is noted by V1, V2, V3. V1 is equal to I1 Z11 plus I2 into Z12 plus I3 into Z13 plus up to IN Zn1n. Next, V2 is equal to I1 Z1 Z21 plus I2 Z22 plus I3 Z23 plus up to IN Z2n. Next, V3 is equal to I1 Z31 plus I2 Z32 plus I3 Z33 plus up to IN Z3n. Now Vn is equal to I1 Zn1 plus I2 Zn2 plus I3 Zn3 plus up to In Zn. V1, V2, V3 up to Vn are the voltage applied to antenna number 1, 2, 3. Next, I1, I2, I3 current flowing in antenna number 1, 2, 3. Next, Z11, Z22, Z33, Zn is equal to self impedance of antenna 1, 2, 3. Next, Z12, Z21, Z13, Z31s are the mutual impedance of antenna 1, 2, 3 and N. This is the voltage and current relations in Yahuda antenna. Next one, V1 is equal to I1 Z11 plus I2 Z12. V2 is equal to I1 Z21 plus I2 Z22. As Z substitute, Z12 is equal to Z21, Z13 is equal to Z31 and V2 is equal to 0 being parasitic. So the equation should be V1 is equal to I1 Z11 plus I2 into Z12. Next, substitute V2 is equal to 0 in second equations. 0 is equal to I1 Z12 plus I2 Z22. I1 is equal to I1 Z12 is equal to minus I2 Z22. From this we got I2 is equal to minus I1 bracket Z12 divided by Z22. Next, substitute I2 values in first equations. V1 is equal to I1 Z11 minus I1 into Z12 divided by Z22 into Z12. V1 is equal to I1, taking I1 common outside, Z11 minus Z12 square divided by Z22. From this we are going to get I1 current. I1 is equal to V1 divided by Z11 minus Z1 square divided by Z2. Like this we are going to follow the same procedure for finding I2. Next, we got the answers of I1 and I2. From this we are going to find Z1, Z2. Next, Z1 is equal to V1 divided by I1. Z2 is equal to V2 divided by I2. Next, in Yahuda antenna does not accept power at any even harmonics, that is second, fourth, etc. Of the fundamental frequency. However, it works with a low value of VSWR, standing wave ratio, on odd harmonics, that is third and fifth. This is because the current distribution of lambda by 2 and 3 lambda by 2 antennas are almost similar. That is, if any fold dipole antenna functions at 20 MHz, it will also function at 60 and 100 MHz frequencies. Since a simple lambda by 2 dipole antenna carries 73 ohm radiation resistance, so it is inconvenient to match it with the feed line of characteristics impedance, that is Z0 is equal to 300 ohm. Then, however, a folded dipole offers terminal resistance of nearly 300 ohm and it is found suitable for such impedance matching. Okay, up to this you are clear. Next, the advantage of the Yahuda antenna. In the following are the advantages of a Yahuda antenna. High gain is achieved in Yahuda antenna. Next, high directivity is achieved. Ease of handling and maintenance. Less amount of power is wasted. Next, broader coverage of frequency. These are the advantages of Yahuda antenna. Next, disadvantages. The following are the disadvantages of the Yagi-Uda antenna. First one should be prone to noise, and second point should be prone to atmospheric effects. Next one, the applications of the Yagi-Uda antenna mostly used for TV reception. Next, second point, used where a single frequency application is needed. Okay, these are the advantages, disadvantages and applications of Yagi-Uda antenna. Then the basic types of dipole antennas. The most common types of dipole antennas are the half-wave dipole antenna. It is a mostly common type of dipole antenna. There are many types of dipole antennas can be designed. Let's explain the major types of dipole antenna in detail. Okay. First one is a folded dipole antenna. Already we discussed, but in general, basic I am going to teach again. A folded dipole antenna is an array of two dipole antenna. If two dipole antennas are connected in parallel to form a thin wire loop, then it is called a folded dipole antenna. As the name implies that the form of dipole antenna is folded back on itself. It is a folded dipole antenna. In the folded dipole antenna, two half-wave dipoles, one continuous and other split at the center, are folded and joined together in parallel at the ends. The split dipole is fed at the center by a balanced transmission line. Hence, the two dipoles have the same voltages at their ends and two identical currents are generated. The radiation pattern of a folded dipole is same as to the ordinary dipole, but the input impedance of the folded dipole is higher and the directivity of folded dipole is bidirectional. This is the basic difference between folded dipole antenna and conventional dipole antenna. Next type is the two-wire folded dipole antenna. If two dipole antennas are connected in parallel to form a thin wire loop, then it is known as two-wire folded dipole antenna. If the radius of both the conductors is equal, then equal currents flows in both the conductors in the same direction. That is, currents are equal in magnitude and phase. If the total current fed at the terminals is I, then each dipole will have current I by 2. Thus, with the same power applied, only half of the current flow in the first dipole, and hence the input impedance increases and it becomes 4 times. Okay, the folded dipole antenna is a very useful and high directivity antenna. Next, general formula for impedance calculation for folded dipole antenna is equal to Z is equal to N square into 73, where N is equal to number of antenna wires. Next, to find the radiation resistance of folded dipole antenna, R is equal to N square into 73. N square, here we are using two-wire folded dipole antenna, so substitute N is equal to 2 square into 73. 4 into 73, finally we get Z is equal to 290 ohm. The two-wire folded dipole can be fed with an conventional 300 ohm open wire transmission line without any matching device. Next, three-wire folded dipole antenna. Three-wire folded dipole antenna is also called as folded tripole. If three dipoles antennas are connected in parallel to form a thin wire loop, then it is known as a three-wire folded dipole antenna or folded tripole antenna. If three-wire folded dipole antennas are used with equal radius, then the equal current flows in all the three conductors. If the total current fed at the terminals is I, then each dipole will have current I by 3. Thus, with the same power applied, only one third of the total radiating current flow in the first dipole, and hence the input impedance increases and becomes 9 times 9 times. The folded dipole antenna, this is the 3-wire folded dipole antenna. Next, thus for a 3-wire folded dipole antenna with equal radius, the input impedance or radiation resistance is Z is equal to RR is equal to N square into 73, where N is equal to 3. So substitute 3 square into 73, 9 into 73, finally we get Z is equal to 657 ohm. Therefore, 3-wire folded dipole or folded tripole can be fed with a conventional 600 ohm 2-wire open transmission line without any matching device. So, the folded dipole antenna or tripole antenna has an important impedance transferring properties. This makes it easy to match with a transmission line that feeds the antenna. It is also possible to change the input impedance by keeping the radius of the two dipoles are unequal. In this condition, a larger current flow through a thicker dipole, and hence we can maintain any desired input impedance. Finally, we are concluding the advantages of folded dipole antenna. Some of the advantages of folded dipole antenna includes: first one, it has high input impedance, hence it makes it easy to match with the transmission line. Second one, it has wideband frequency, that is wide bandwidth, hence it is suitable for FM and TV broadcasts. Third one, it has high gain and high directivity compared to a simple dipole antenna, hence it can used in the Yahyuda antenna. Next, FM dipole antenna. FM dipole antenna is defined as a vertically polarized half-wave dipole antenna. The FM dipole antenna is mostly used as its to build, and it is suitable to provide improved reception of very high frequency FM broadcast. The radiation pattern of FM dipole antenna is perpendicular to the axis of the antenna, that is, it is horizontal because the FM dipole antenna is a vertically polarized half-wave dipole antenna. Next, the radiation pattern of FM dipole antenna should be perpendicular to the axis of antenna. Next, the FM dipole antenna is generally used for FM broadcasting. The frequency range between 88 MHz to 108 MHz. Next topic, fan dipole antenna. Fan dipole or multi-band wire antenna is one in which multiple dipoles are connected with a common feed line and they are spread out like a fan. Hence it is called as a fan dipole antenna. As the name implies that the form of fan dipole antenna looks like a fan, it is also known as a parallel dipole antenna. Next,